Welcome to Tomorrow Unveiled. I'm your host, and today we are zooming in on a very specific moment in time. This week, January 19th, 2026. Now, if you just glance at the calendar, it looks like any other week in January. But if you look at the stack of reports, the regulatory filings, and the physics preprints that have landed on our desk this week, I think historians might actually look back at this window as a genuine tipping point. For the last 20 years or so, the energy transition has been defined by a single dominant philosophy: harvesting flows. We built windmills to catch the breeze. We built silicon panels to catch photons from the sun. We were essentially high-tech farmers harvesting the weather. But looking at the signal coming out of the noise this week, that era is shifting. We're moving from harvesting flows to mastering cores.
That is the only way to describe it. It's a phase transition. We are moving from expensive energy spreading out over vast tracts of land to catch diffuse energy to intensive energy, density, intensity. And frankly, looking at the data our research team has compiled, we just don't have a choice. The grid is under siege.
Let's talk about that siege for a second, because we keep hearing this phrase, the age of electricity, and it sounds like a marketing slogan from the 1950s. But the numbers behind it are, well, they're actually terrifying if you're a grid operator.
They are. We are seeing a demand curve that is, it's breaking every model we had even 5 years ago. The projections highlight that electricity demand is set to surge by nearly 40% in less than a decade.
40%.
Yeah. We haven't seen a slope like that since the post-war industrial boom. And we need to be really clear about what's driving this. It's not just you and me buying an electric SUV. It's the industrial electrification of the economy making steel and chemicals with electrons instead of fire. And above all else, it's the gigawatt-scale data centers required for artificial intelligence.
Which brings us perfectly to the title of today's deep dive for Tomorrow Unveiled: Green Code, Hot Core. It sounds a bit like a cyberpunk novel, but it's actually describing a feedback loop that has really emerged this week.
It's a perfect description. Green code refers to the explosion in exascale computing, AI, and, open source simulation that allows us to model physics with unprecedented accuracy. Hot core is the result of that modeling. The resurgence of high-density energy sources, fusion, advanced fission, and deep geothermal. The thesis here is that you really can't have one without the other. The AI needs the massive power, so the AI helps us design the reactor to generate that power.
It's a symbiosis.
Right.
Or a snake eating its own tail, depending on how cynical you want to be about the tech industry.
Let's stick with symbiosis for now. It's a bit more productive.
Fair enough. So to help everyone navigate this, we've broken this massive news dump into 3 main pillars. First, we're going to look at a physics-defying breakthrough in nuclear fusion that happened just days ago. And, scientists didn't just nudge a record, they broke a fundamental law that has held the field back for decades. Second, we're looking at the nuclear renaissance, specifically the SPEED Act, and how factory-built reactors are finally moving from PowerPoint to the real world. And third, we're going to talk about turning the Earth itself into a battery with next-gen geothermal.
It's a packed roadmap, but every single one of these stories connects back to that central theme: density and computation. Doing more with less physical space, all enabled by better code.
So let's start there with the code. We have this fascinating report from our research team about digital twins and this green code revolution. Now, I have to play devil's advocate right off the bat here. We've had computer-aided design CAD for, 40 years? We've had flight simulators for decades. Why is simulation suddenly the headline story for 2026? It feels a little like a buzzword.
It does feel like a buzzword until you look at the nature of the problem we're trying to solve. Designing a wing for an airplane is hard, but it's what we call a deterministic problem. Air flows over metal. We understand the Navier-Stokes equations of fluid dynamics almost perfectly. If you run the math, you know what the air is going to do. Designing a nuclear reactor is a different beast entirely. You're dealing with neutrons.
Subatomic particles.
Billions and billions of them. And neutrons, they don't flow like water. They bounce, they scatter, they crash into atomic nuclei and can change the element itself. That's transmutation. They cause something called embrittlement, essentially aging the steel and concrete around them incredibly rapidly. Historically, you just couldn't calculate that with perfect accuracy because the math was, well, it was too heavy. It's probabilistic, not deterministic.
Meaning you can't predict exactly what any single neutron will do.
Exactly. So for 70 years, what did we do? We built expensive physical prototypes. We'd turn them on, watch them vibrate or leak or get brittle, and then we'd go back to the drawing board. It was pure trial and error, and it cost billions of dollars and took decades.
And this is where that software package our team highlighted, OpenMC, comes into the picture.
Yes. OpenMC is a total revelation because it uses something called the Monte Carlo method.
Which I'm guessing is named after the casino.
It is, and for a very good reason. It's all about rolling the dice. Instead of trying to solve one giant, impossible equation for the whole reactor, the computer simulates individual neutrons. It rolls the dice. Okay, this neutron hits a graphite atom. Does it bounce? Does it get absorbed? Does it cause fission? You do that 1,000,000,000,000 times, and a statistical picture emerges that is incredibly, incredibly accurate.
But to do that 1,000,000,000,000 times for a complex reactor geometry,
Yeah.
you need some serious hardware. You can't run that on your laptop.
Not even close. You need exascale computing. We are talking about computers capable of a quintillion calculations per second.
A quintillion.
That's a billion billion. The research shows that scientists are now running these virtual experiments where they simulate the entire life cycle of a fuel rod or the stress on a fusion reactor wall over 20 years, all in a matter of days inside the computer.
So before they even think about pouring a single cubic meter of concrete, they know if the design works.
And more importantly, they can de-risk the design. Investors are terrified of nuclear projects because historically they run way over budget and over time because of unforeseen technical snags. If you can solve those snags in the green code phase, the physical build, the hot core, becomes an investment proposition, not a gamble. It completely changes the capital efficiency of the entire industry.
Which is the perfect bridge to our second segment. Let's talk about that hot core. Because while the simulations are running these cool digital loops, the physical reality is getting hotter. And this week, frankly, looking at this fusion news, I had to reread the brief 3 times. We had to talk about the Greenwald density limit.
The Greenwald limit. This has been the headache, the speed limit, the absolute bane of fusion scientists for 35 years.
Okay, break it down for us. What exactly is this limit, and why should someone who isn't a plasma physicist care about it?
Okay, let's visualize a tokamak. That's the donut-shaped machine where we use these incredibly powerful magnetic fields to trap a gas that is heated until it becomes plasma hotter than the center of the sun. To get energy out of that plasma, you need to fuse the atoms. And to get them to fuse, you need them to collide.
So you need to pack them in tight. You need density.
Precisely. But what Martin Greenwald observed decades ago was that there was a hard ceiling. If you pushed the plasma density past a certain point, the plasma would suddenly become turbulent. It would disrupt. Essentially, the magnetic bottle breaks, the plasma smacks into the wall, cools down instantly, and the reaction just dies.
So it's like trying to overstuff a suitcase.
Oh.
Eventually, the zipper just bursts and your clothes fly everywhere.
That is a surprisingly accurate analogy. And this was a tragedy for the economics of fusion. Because here is the key formula you need to remember. Fusion power increases with the square of the density.
Wait, the square. So if I double the density.
You get 4 times the power output. If you triple it, you get 9 times the power.
Wow.
Density is the master knob for commercial viability. As long as we were trapped below that Greenwald limit, reactors had to be gigantic and gigantically expensive just to generate net energy.
And the news this week is we broke it.
We didn't just break it, we smashed it.
Yeah.
The research team identified a major finding from the East Reactor team, the Artificial Sun Project. They achieved what they're calling a density-free regime. They pushed the plasma density far beyond the Greenwald limit, and it stayed stable.
How? I mean, did they just build stronger magnets or something?
No, and this brings us right back to simulation. It wasn't about brute force. It was about finesse. They discovered that the instability wasn't some inherent law of physics deep inside the core, but it was a result of how the plasma interacted with the walls of the reactor.
The edge conditions.
Exactly. By optimizing that edge interaction, essentially keeping the container incredibly clean and managing the magnetic fields at the very fringe to prevent impurities from getting into the core, they prevented the crash.
So the speed limit wasn't on the car itself, it was on the road conditions.
That is a brilliant way to put it. And now that they've repaved the road, we can drive much, much faster. This changes the economics of fusion overnight. It means future commercial reactors can be smaller, cheaper, and way more powerful than we assumed even 5 years ago.
And speaking of commercial reactors, it's not just the big government labs anymore. I'm seeing some news here about pixels and stellarators. This sounds like we're moving away from the classic donut shape.
We are seeing a divergence in design, which is really healthy for the industry. Thea Energy, a U.S. company, just got a major nod from the Department of Energy for their pilot plant. They're using what's called a stellarator design.
I've seen pictures of stellarators. They look like these twisted, almost melted slinkies. They look impossible to build.
Traditionally, they were. They require these incredibly complex, twisted magnetic coils that have to be manufactured to millimeter precision. It's a manufacturing nightmare. But Thea Energy is doing something radical. They are replacing those complex coils with hundreds of small, simple, flat magnets.
Like pixels on a computer screen.
Exactly like pixels on a screen. Instead of one giant fixed magnet, you have an array of hundreds of small ones, and use AI to tune them in real time to shape the magnetic field perfectly. It simplifies the construction massively because you're just using standard parts to create a very complex field.
It's fascinating to see how the hardware itself is becoming software-defined.
Oh.
But let's look at the global race here. We had the breakthrough in China with the East reactor. We have this pixel fusion concept in the US. And then I see Bavaria in Germany, of all places, is making a huge play.
Yeah, that one caught a lot of analysts by surprise. Bavaria announced a plan to build not one, but 3 fusion reactors. They're looking to transition from pure research to commercialization by the early 2030s.
Early 2030s. We used to have that joke that fusion is always 30 years away.
That joke is officially retired. With the kind of funding we're seeing, like the $143 million Series A for Star-Taurus fusion in China just this week, and the government support in places like Japan opening their national labs to private startups, the timeline has just compressed. We are looking at commercial pilot plants likely breaking ground before the end of this decade.
That's incredibly rapid. It really feels like the starting gun has finally gone off.
It has, and the prize is infinite, clean, firm energy. It's worth the race.
We're going to take a quick breath here because I want to give our viewers on YouTube a chance to join this community. If you're finding this insightful, please take a moment to like this video, subscribe to Tomorrow Unveiled, and consider hitting that new hype button to help us reach more viewers. And of course, be sure to turn on notifications so you never miss an update on the future. Okay, we're back. We've talked about the code and the future core of fusion. But let's be real for a second. Fusion is the 2030s. We have a power crisis today. We need to talk about what is happening right now, on the ground, with nuclear fission. Because while fusion is the dream, fission is the workhorse. And it seems like that workhorse is getting a massive makeover.
It's the nuclear renaissance, or as some people are calling it, the industrial nuclear era. We aren't just building cathedrals of power anymore, we're building appliances.
Small modular reactors, or SMRs. I feel like we've been hearing this acronym for a while now, but this week there was actual money and, more importantly, actual law moving.
The money is significant, don't get me wrong. The government just announced an $800 million investment to jumpstart SMR deployment, specifically targeting the Tennessee Valley Authority and Holtec. But honestly, the money is secondary. The most important thing that happened this week is the SPEED Act.
I do love a good legislative acronym. Standardizing, permitting, and expediting economic development.
It passed the House recently, late 2025 or early 2026, depending on when you track the vote, but the implications are hitting right now. This is a direct attack on red tape.
Right, because traditionally building a nuclear plant involves years and years of environmental reviews, lawsuits, and delays before you can even dig a hole.
Correct. The National Environmental Policy Act, or NEPA, was designed to protect the environment, but it has often been used as a tool to stall clean energy projects indefinitely. The SPEED Act sets firm deadlines on those reviews. It limits the time frame for litigation. It basically says you can't sue a clean energy project to death.
That sounds great for developers, but I have to imagine it's controversial. I mean, we're talking about bypassing environmental reviews for nuclear power.
Oh, highly controversial. And there is a real tension here. Environmental groups are rightfully worried that we might bypass critical protections or ignore local community concerns. But the counterargument, which is gaining a lot of bipartisan traction, is that climate change is the ultimate environmental threat. If it takes 10 years just to permit a clean power plant, we lose the climate war. The SPEED Act is trying to balance that, accelerating the good infrastructure while trying to maintain safety standards. It's a calculated risk for sure.
And this acceleration is so crucial because these SMRs aren't just little versions of the big plants we already have. They do something different.
Yeah.
I was reading the notes on X-energy and this concept of industrial heat.
This is a nuance that most people miss, but it's absolutely vital. We talk about electricity, but a huge chunk of global carbon emissions comes from making things steel, concrete, chemicals, paper. These processes need heat, really high heat, 700 degrees Celsius or more.
And solar panels don't give you 700 degree steam.
They don't. And taking electricity, then turning it into heat, and then putting that heat into a furnace is incredibly inefficient. You lose energy every time you switch forms. But the X100 reactor from X Energy does something different. It produces heat as heat. You can pipe that 750 degrees Celsius steam directly into a Dow chemical plant, bypassing all that efficiency loss.
So it creates a localized industrial ecosystem, a clean energy industrial park almost.
Exactly. It decarbonizes the sectors that have always been called hard to abate.
And then there's the water aspect. I saw Niscale is working on using SMRs for desalination.
This is what our team called a win-win-win finding. You use the reactor to power reverse osmosis, turning ocean water into fresh drinking water. That process leaves behind a really salty brine. Usually that brine is a waste product that's toxic to marine life if you just dump it back in the ocean. But Niscale found a way to use the extra heat and electricity to process that brine into clean hydrogen.
So wait, you get clean power, clean water, and clean hydrogen fuel, all from one factory-built unit.
Precisely. It turns a liability, the waste brine, into a valuable asset. It's the definition of a circular economy.
It's incredible how the technology is pivoting from just making electricity to solving resource scarcity.
Speaking of resources, let's look down, way down, segment 4, the Earth as a battery.
Geothermal, the sleeping giant of clean energy.
I have to admit, I always thought geothermal was just for places like Iceland or Yellowstone. You know, you need a volcano or a geyser in your backyard.
That was Generation 1 geothermal. We are now entering the era of enhanced geothermal systems, or EGS. And the mantra here is pretty simple. Hot rock is everywhere if you drill deep enough.
And thanks to the oil and gas industry, we are really, really good at drilling deep. That's the irony of this century, isn't it? The very technology developed for fracking to extract fossil fuels is now being used to save us from them. EGS uses those precision drilling techniques to go miles down into hot, dry rock. They fracture the rock, just like in fracking, and then circulate water through those cracks to pick up the heat and bring it back up to the surface.
So we're basically hacking the Earth's crust.
Effectively, yes. And this isn't theoretical anymore. We have a project in Utah, Cape Station, which is slated to bring utility-scale power to the grid this year, in 2026. This is a huge milestone because it proves EGS works at a commercial scale. It transforms geothermal from a niche volcano tech into a truly global solution.
So what's the potential scale we're talking about?
Our sources suggest this technology could supply 20% of U.S. electricity by 2050. And the best part? Unlike wind or solar, it's 2047. It doesn't care if the sun is shining or the wind is blowing.
It's firm power. It's the base load that we need. But let's say we do need to store energy from those intermittent sources. I saw something in the notes about the sun in a box, which frankly sounds dangerous.
It's safer than it sounds. We're talking about thermal storage. If you have excess solar or wind power, you don't always have to put it in a lithium-ion battery. You can store it as heat.
There's an Australian company, 1414 degrees. Why that specific number?
That is the melting point of silicon, 1,414 degrees Celsius. They are literally using molten silicon to store energy.
Silicon, as in sand.
Basically, yes. It is incredibly abundant, it's cheap, and it holds heat incredibly well. When you have cheap solar power at noon, you use it to melt a container of silicon. When you need power at night, you extract the heat to run a turbine. It exploits what's called the latent heat of that phase change from solid to liquid.
So it's a battery that doesn't really degrade.
Correct. Chemical batteries degrade a tiny bit every single time you charge and discharge them. Molten silicon just melts and hardens. It can do that almost indefinitely.
And then there's the desert tech. I saw HALEU debuted something at the World Future Energy Summit designed specifically for 50 degrees Celsius heat.
This is critical. Standard lithium batteries hate heat. If you put a battery farm in the middle of the Saudi desert, you have to spend a huge amount of energy just air conditioning the batteries themselves so they don't explode or degrade. HALEU developed a liquid-cooled storage system that is designed to survive and thrive in that exact environment.
It makes perfect sense. We're generating the solar power in the desert. We should be able to store it there too. But who is buying all this? Who's driving the demand for silicon batteries in desert storage?
And that brings us to the customer, the entity that is reshaping the entire grid, the data centers.
We saw a massive deal just this week. Meta, the parent company of Facebook and Vistra.
This is the signal that the market has fundamentally shifted. Meta signed a 20-year agreement to buy power directly from Vistra's nuclear plants.
20 years. That's
Okay.
a lifetime in the tech world.
It is, and it tells us two really important things. One, big tech has realized that to win the AI race, they need firm power. They cannot rely on the vagaries of the weather. They need 5 nines of reliability, 99.999% uptime. If a training run for a new AI model gets interrupted because the wind died down, they could lose millions of dollars and weeks of progress.
So they're willing to pay a premium for that nuclear reliability.
They absolutely are. And this capital injection allows operators like Vistra to extend the life of these plants and even upgrade them. The tech giants are effectively underwriting the nuclear renaissance.
And this completes the feedback loop we started with at the top of the hour.
It does. AI demands more energy. This demand creates a new, high-value market for nuclear and geothermal. But at the same time, the AI, the green code, is what allows us to design the efficient new reactors, the hot core, to generate that energy in the first place.
It's actually a really optimistic take. We so often hear that AI is an environmental disaster because of its energy use. But you're arguing that the pressure from the tech sector is actually funding and accelerating the clean energy transition faster than government policy alone ever could.
I am. I think AI is the forcing function. It is forcing us to stop simply harvesting the flows and start mastering the cores.
That is a perspective shift I think we all needed. So let's wrap this up. Green code, hot core. What is the summary for our listener today after all this?
The summary is that we are moving toward a high-density, digitally optimized energy future. We are leaving the era of simply scavenging energy from the wind and sun, though they will remain vital parts of the mix, and entering an era where we engineer our energy at the atomic and subsurface level. The convergence of fusion, SMRs, and geothermal offers a path to abundance, where we don't just cut emissions, but we actually expand our energy capacity to do incredible new things.
Abundance. That's the key word here. We aren't just trying to keep the lights on. We're trying to power a civilization that does more. Which leads me to our closing thought for everyone. We spend so much time debating the cost of energy. Is nuclear too expensive? Is storage too pricey? But with these hot cores coming online and AI optimizing the code to build them, we might soon need to ask a very different question. The question isn't, how do we afford the energy? The question is, what will we build when clean, firm energy is no longer the bottleneck, but the catalyst?
That is the question of the century.
If you're listening on a podcast service like Apple Podcasts or Spotify, we'd be incredibly grateful if you could leave us a rating and review for Tomorrow Unveiled. It truly helps us reach new listeners. And we love hearing your thoughts. Whether you're on YouTube or your favorite podcast app, leave a comment and let us know what you think about the hot core revolution. Are you betting on fusion or geothermal? I think I'm putting my money on the pixels. Until next time, keep looking forward.